Welcome to Maths with EJD. The playlist is numerical optimization techniques. The the subtopic we are considering are derivative free derivative free numerical optimization methods. Okay, we've considered previously gradient-based methods. Now, derivative-free methods do not require you being able to differentiate an expression or the function the objective function you're trying to optimize. So, for the derivative-free methods, in the previous video, I had talked about the nail-the-mead method, nail-the-mead method. So which talks about so you have an initial simplex, which is a triangle in a two-dimensional system, and a tetrahedron in a three-dimensional system, and then you begin to search for the best point, and then of course we'll always finish things up with Python. So now that mid method. The next will be the what we know as genetic algorithms. That's based on genetics and biology. So genetic algorithms. Okay. And then finally, we have the simulated annealing method. Simulated annealing. Annealing is a metallurgical idea, right? Simulated annealing. So now you can see the methods are really interesting. Nelda-Mead is from geometry, genetic algorithms is from biology, and simulated annealing is from metallurgy. And of course, in the previous video, we had taken care of the Nelda-Mead method. So the focus now shifts to genetic algorithms. Genetic algorithms as derivative-free numerical optimization technique. Okay, so let's see what that holds for us. Overview. So genetic algorithms, GA for short. So after now, I'll just say it's GA. Genetic algorithms are optimization, optimization techniques inspired by natural selection, because that's a biological thing. Natural selection, I think popularized by Gregor Mendel or something. I'm not sure. I mean, I think it's Gregor Mendel or someone like that. Okay. So they evolve solutions, iteratively using genetic operators, using genetic operators. And the genetic operators are selection, crossover, and mutation. These are genetic things, right? Genetic operators like crossover, selection, crossover, and mutation. Okay, so you have mutation happening. Like you want to get the best. I mean, these days we have a lot of talk about genetically modified um uh GMOs, talking about food, right? So sometimes people try to recombine genes to get a particular kind of outcome. So that idea has been brought into optimization. So steps in genetic algorithm. So it's more like you're engineering a process. So of course, as usual in numerical analysis, in most numerical processes, we have to initialize. You need an initial guess, like initial. So you have a starting point as the initialization. And for initialization, right? So here you generate a population, generate a population of candidate solutions, population of candidate solutions. That's the initialization process. And afterwards, you talk about evaluation. So you evaluate those candidates of evaluation. So you evaluate them. So here you assess fitness, using an objective function. So it's a bit close to what we did under nail that meets method. So assess fitness using an objective function, which you either want to minimize or something. So using an objective function, okay. Then step 3 is about selection. So after you have evaluated, you want to select the best. So choose the best individuals. Choose the best individuals for reproduction. Okay. Then in step 4, you have what's it called crossover or recombination. That's the whole genetic thing. Crossover or recombination. So here you combine parents to create offspring. Combine parents to create offspring. These are biology things, right? But then we're applying to optimal control or optimization. In step 5, you mutate. Talk about mutation. So for mutation, right, you introduce small small random changes for diversity. Okay. And after doing that, you go for the last step. Of course, we always want to end the process at some point, right? That is termination, and you need some criteria for this as usual. So termination. So what you do here is you repeat as usual, repeat until a stopping criterion, is met. It could be the number of iterations, like I would like to say. It could be like max generations. Maybe you have got the best generations you can ever get, or a particular number of generations you want. And it could also be about convergence of, as you evaluate the functions, you want to see maybe the functions are getting closer and closer together. So that gives you a clue that you have almost got where you need to get to. So now let's do this and this. Okay. Let's take an example as usual to drive home the point. Example. So let's maximize f of x, which is equal to x squared. Very simple, just this simple parabola with x lying in the closed interval 0 to 31. Okay. So we want to maximize, we want to get the best value of that function, right? So of course it's a random choice, right? But what we are going to do is using a 5-bit binary representation, 5-bit binary representation, okay, for x, we evolve the best solution. You know, it's about evolution. We evolve the best solution, okay? So, and then with that, we move on step by step. We go for step 1, which talks about the initial population. So initialize population. So we've said that we are going by 5-bit binary representation. So we just randomly generate a population of 4 individuals. A population of 4 individuals. And look at the individuals now. We have 10110. That's actually 22 in reality. So, and if we evaluate at that point, so this implies that f of 22 is equal to 484. You know, the function f of x equals x squared. So f of 22 is 484. So another individual, you know, these are random individuals, right? So we have 0, 1, 1, 0, 1. Okay. So, and 0, 1, 1, 0, 1 is 13 in base 10. That is f of 13. F of 13 is 169. Now, I mean, one thing you should be clear about is that this example is actually a very simple example, right? It's in reality, right? The problems are more complicated than this. For a fact, f of x equals x squared is you can easily differentiate it to get 2x, and then you can put a value to get whatever to find the minimum or maximum or whatever you want to find. But here we are just using it to explain the idea, but it handles more difficult issues than this, right? So we have two random individuals. The third random individual is 11011, which is actually 27. And if you do f of 27, you get 729. And then you have 00010. That is simply 2. That means f of 2 is equal to 4. So that is that's the initialized population, right? Okay, so the next step now is the selection step, step 2. So we want to see the best performance up there. So we have a selection, and with that, we roll a roulette wheel for selection, more like a raffle draw, so to speak. So from here now, we get total fitness. So we get total fitness to be equal to 484 plus 169 plus 729 plus 4, and all of that is equal to 1386. Okay, so we'll now say higher fitness values have higher selection probability. Higher selection probability. Then from there, you assume we pick, assume we pick 10110, which is 22, and we pick another one. We pick 11011, which is 27, as we see up there. So assume we do that now. So the next step we go to is the crossover step. So we go for step 3, where we talk about crossover. We talk about selection, crossover, and mutation, right? So we go for crossover. So let's see crossover at position 3. Crossover at position 3. So what's going to happen? We've picked 22 and 27. That's 10 at position 3. Now we have a crossover 10110 plus the second one, we have 11011. So that's 110 after position 3, 11. Okay. And if you cross things over like this, what do we get? So we get 10111. Okay. So this is this 10 and this 11 like this. And then another possibility we can get is would be this one, 110 and 10 like this. So this is 11010. All right. So from there we have crossed over, and then we are going to have two new possibilities. We have 10111, and that tallies with 23. Okay. And then we have 11010, which tallies with 26. Okay, so of course we can evaluate all of this and see what the functions look like. So we have those two crossovers. Then so the next step talks about mutation, step 4. We are not doing anything with this for now. So we have step 4, where we talk about mutation, where we throw in some randomness. So flipping a bit in 11010, that's here now. So if you flip that a bit, we can get something like so we just change something randomly. So let's change the second value. We have 10010, and that tallies with 18, right? That's some kind of mutation happening right there. So we flipped that over. So we have 10010. So we go for step 5. Step 5. In step 5, we evaluate and repeat. So we keep doing this, evaluate and repeat. So what's happening here is we now have new generation. So we have new generation. So for the new generation, we have 10111. we obtain this from crossover. We also have, so now we evaluate f of 23, that's 529. Then we also have another one. We have a kind of mutation happening, crossover and then mutation. So 10010, 10010, which gives 18, such that f of 18 is equal to 324. So that's like a process already, but then we keep doing things like this we get until we get a convergence. But at this point, I want to go and finish things up with Python. Okay. So I come to Python. So you see that we have, so we import random because randomness is involved here. So you can see we just pick some individuals at random, like we saw there. So the population size is 4, you know, and the chromosome length is 5, talking about the 5-bit binary. So you can choose any other chromosome length depending on what you choose. Then the mutation rate is 0.1, that's probability of mutation. The generations will be 10, that's number of generations. Target fitness is 31 squared. So the optimal fitness value. So that will maximize x squared for x equals 31, right? So because if you put 31, you get that's where you get the highest. Like normally, just like I said, this problem is very simplistic and it is just for explanation of what genetic algorithm looks like. So normally it should handle something more difficult that cannot be differentiated. For sure, X squared can be differentiated. So you generate initial population. That's what you have in line 16. So define initial population and return random from 0 to 31 like that. And then you do selection using roulette wheel. So that selection we did the other time. So we just picked two randomly. And then you go for the crossover. I demonstrated that clearly enough. And that is what the part of the code from lines 26 to 31 is taking care of that. Then the mutation part where maybe a 1 just turns to 2 or a 0 turns, a 1 turns to 0 or a 0 turns to 1. Then you have in 40, you talk about genetic algorithm with elitism. So you want to get the best of the best, right? So you define this genetic algorithm, you have the generations, the best solution, none, best fitness. So you store the best fitness value for visualization, and then you pre-compute fitness for the initial population, and that goes on. Then you find the best individual in the population of elitism. So the best of the best you pick, and then while in that lens, you do population size. So the whole thing continues. So you can study this code. You can find it on Facebook. I'm not able to put it on YouTube because of the of some kind of special maybe some square brackets or something like that. So, and then at the end of the day, if you run it, you get best solution, the total generations, best fitness values, for the genetic algorithm. And then you have a bit of visualization here. So if I run this, see what we get. Okay. So you see, generation 1, the best is 28, which leads to 784. Okay. Then if you go to generation 2, the best in generation 2 was 30. So you can be sure that in each generation you get something better than the previous one. And that makes sense too, right? In the case of reproduction, like you discover that children are most likely more beautiful than their parents. Their parents are more beautiful than their grandparents and things like that. So that's the idea of genetic algorithm. So generation 1, the best the function gave is 784. Generation 2 gave 900, and generation 3 gave 31. So in 3 iterations, we get to the maximum level where x equals 31 and f of x is 961. So you see that movement happening like that, So the best solution found is x equals 31 and f of x is 961. So the total generations is 3 to achieve that elitism, to achieve that best of the best kind of situation. Okay. So that's the Python code for our demonstration. So let's go for conclusion and probably practice questions. So in the conclusion, right? Conclusion. So we see that genetic algorithm efficiently explores solutions, okay, filtering out inferior results. So genetic algorithm efficiently explores solutions, balancing 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 exploitation. So exploitation is what you can refer to as selection, this situation, balancing exploitation and exploration, which is mutation, like you're experimenting with things. So it is widely used. It is widely used in optimization, scheduling, and machine learning. Okay. So those are use cases for genetic algorithms. So it's been quite such a nice evolutionary process. So let's see if we can get some practice questions. Okay. Um, Practice questions. So of course, I'll just dictate. Explain the role of selection, crossover, mutation in a genetic algorithm. Why is mutation necessary in genetic algorithm, and what happens if its probability is too high or too low? Three, compare roulette wheel selection and tournament selection in um genetic algorithm. How does genetic algorithm differ from traditional optimization techniques like gradient descent? What stopping criteria can be used to terminate a genetic algorithm? So let me see one where I can actually use a particular um, mm, okay, let me just drop this one question and leave it at that. So perform roulette wheel selection. Perform roulette wheel selection for a population with fitness score, with fitness scores 120, 300, 180, and 400. Okay. So then show the probability, show the probability of selection for each individual. Yeah, that may be a bit off the cuff, but you want to think that up and see what happens. Okay, so we have that, right? Okay, there's a question I saw that why is mutation necessary? And in genetic algorithm, what happens if its probability is too high or too low? I think we can experiment that with our Python code. So let's say our Python code. So if the mutation probability here is 0.1, what if it is something like 0.9? What happens? How does it affect the process? Okay, the thing is that so if mutation probability is high, you see that it's easier to get to the best result in a shorter. So this happens in 2 generations now because the mutation probability is higher. Okay, I think that's one answer to our question, right? So a high mutation probability will make us achieve the result faster. So now the mutation probability is 0. It's 0.5, I believe. I think it's 0.5. Why is it okay? It's 0.5, and then we still have it. We have this happening in 4 generations. Okay. Like that. So I mean it affects how fast we get to the optimal solution. So of course you have the practice question there. You can put it in the comment section either on YouTube or on Facebook. You can find the code on Facebook. As I said, so you can copy out the code, put it on your own IDE, and tweak it and see what happens as you change different parameters in the process. So you can also comment. Let me know how helpful these videos are. Let me know also if there's a topic you'd like me to teach you, a problem you'd like me to solve. If you have subscribed to this channel, thank you so much for that. If you haven't, please go ahead and do that and hit the notification bell so you can always get alerted each time a new video is released. In the next video, I'll be talking about simulated annealing, which is another derivative-free method of talking about numerical optimization techniques, all right? So like and share this video also so that more people can have access to this great learning. Till I come your way again, keep doing maths right. Bye.